No.
Let's get started. So just standard reminders, there's a lab this week, Lab 9, and Lab 10. I'll talk a little bit about the Lab 9 output analyzer today, so there'll be a little bit of a preview to that if you haven't looked at it. Otherwise, you should be able to handle it with the slides. If I can put together a tiny tutorial on the output analyzer, I will, but there's not a whole lot to it, which is why I haven't been as focused on the video for this lab. The slides I think are pretty self-explanatory. After this week and next week, then the next 2 weeks are just open labs for your final project. Your final project is so hopefully you've gathered data and you feel pretty good about your project. If you're still having trouble kind of formulating what you're looking for, we'll hopefully be able to give you some feedback that will be helpful from your input modeling report. Otherwise, if you actually go into Chapter 9 of the lecture book, exercises 1 through 5, they have some examples of things that you might measure in a number of different systems. You could give some other examples here, like the walk-only zones on campus, different intersections, coffee shops, etc. So just if you're still having trouble kind of formulating what the question is, let us know, and then hopefully that'll be a little more clear as we're reading through your input modeling reports and giving that feedback back to you. So then the next deliverables for the final project are not until the final week of classes, and that's your project, that's your presentation. And then the Saturday after that, so in between the last week of classes and finals week, will be that final project report. So we'll pretty much leave you alone for a while. Questions?
So in the advanced lab, are we going to talk at all about OptQuest or anything like that, or that will be something to learn?
I'll mention OptQuest a little bit this lecture, and I don't remember in Lab 10 if we specifically have you do an example of OptQuest. I don't think, because it's a little, it's not that much more involved, but I think we just, in this unit, I will mention it at least once or twice, and it's been, I think, mentioned in the ICAs, or at least it will be if it hasn't already. But OptQuest, yeah, I'll definitely plug it here, but we may not do anything hands-on. It might be kind of on you, but I'll at least introduce it. So any other questions about the project or the schedule moving forward? All right, so other assignments, there's just sort of 2 ICAs left before the final review ICA. So J3 is available. It's more over this output performance stuff. And then ICAL will be the last kind of new content one. And then the last ICA, which is ICA-M, has been released when ICAL is after it's due, and that's a final exam review, which is just like the midterm one, where it's just going to collect all the questions for the previous ones and maybe add a couple more and sample randomly from it. You can take it as many times as you like, et cetera, et cetera. So very similar to the midterm. And also don't forget, it'll be a similar retake schedule with the final exam. So in the last week of classes, we'll have what I'm calling a pre-take, which will be a final exam just like kind of the first midterm. And then, depending on your performance on that, you can choose to come in during the final exam week and take the true final exam. But in reality, it's a retake. I just think it sounds better to call it a pre-take and a final. And then also on Thursday, there will be somebody I'm partnering with, an education research group here on campus that it's in sort of STEM education. So there'll be a postdoc from that group will come in and introduce this retake schedule. We don't think a lot of other people, at least in CIDSE, are doing that, and so we're interested in adding it onto a study that they're doing. And so if you're interested in your scores contributing to that study, and anonymously, then she'll introduce. Basically, there will be a consent form that if you want your data to be included in that study, you'll be able to sign that consent form electronically, and I'll actually provide a little bit of extra credit for those who actually fill out the form, regardless of whether you're participating or not. So, but all that'll be detailed on Thursday. So I'm trying to make an argument that these retakes have potentially good, they're good for learning outcomes, and so your data could help go into that. So hopefully you'll be interested in participating just by contributing your scores. So, but we'll talk more about that on Thursday. The current homework that's out is this G3, which again is the question 1. Hopefully that's actually felt like something right out of 380 or 385. And then question 2 is this power analysis stuff, which we covered a lot last time and the time before that. And there's a video on Canvas for extra help. Question?
Do we have any tests for when we can't follow the independence assumption?
So like you have a bunch of data that actually will come up a bit in how we handle those cases will kind of be a part of this unit. So we'll hopefully answer your question. If we don't, then we'll maybe circle back then. And then the final homework will be an arena-based assignment, J2, and that one is actually something we use to capture some ABET data, so there won't be a solution set for J2, but this is basically going to go into the inventory management problem that you've seen in one of the previous labs with Bucky. You'll make some modifications, and then you'll do kind of an optimization where you'll say, all right, so what should the little s and the big S be in order to optimize performance? And so you'll go through that, and again, then your scores for that go into ABET matrix to see, are you learning things relative to the previous semesters? So any questions about administrative stuff? All right, so so where we've been is kind of looking at this plot for a lot of the basic last lecture too. This is effectively, hypothesis testing is formalizing the idea that if you take a bunch of observations and they all look a little too weird, how do we say how weird is too weird? And so we have sort of a normal, when I say normal, and I mean not necessarily normal, but we have our expected distribution of observations, and we have observations that either come from that distribution or come from another distribution. And if we take multiple ones of those observations and say average them together, then maybe they end up landing on one side of a threshold or another. And if they land on the one side of the threshold, you say it's a little too weird and we're going to reject whatever we thought was the null, and if it lands inside, we're going to say, well, it's consistent. We don't necessarily know if it came from a different hypothesis, but at least it's consistent with what we assume to be true, and that's hypothesis testing. And so, at least in scientific disciplines, we set this threshold based on a false positive rate of 0.05, and we set our statistical power to be 80% or higher. Those are just the two conventional numbers that if nobody tells you, those are the numbers you should use, 0.05 and 80%. But as we'll mention here in a bit, that in engineering, sometimes we can play with this a little bit because our goals are a little bit different than kind of scientific goals. So what does this look like? We talked about the t-test and tried to go into the roots of what's going on with a t-test and said you could only use a t-test if you've got data that are normally distributed and all the samples are independent. Under those conditions, then if you take an average of a bunch of data, that average becomes a sample, and then your question is that sample too far away from your hypothetical mean than you might expect from the norm, from the distribution that you would expect from samples taken from your hypothetical distribution. And because your hypothesis is purely a parameter, then the t-test is what we call a parametric test. So there are non-parametric tests which don't make any assumptions, but the t-test requires the normal distribution, so it's a parametric test. And so graphically, the t-distribution looks a little like a normal distribution, but it doesn't get very normal until you get really high degrees of freedom. Otherwise, it's got these kind of tails, which are a lot higher, and the mode is a lot lower. And again, this is sort of summarizing what I just said, but if I sort of say again graphically here, if this blue line is what I would expect from my t statistic, if I'm actually operating under the hypothesis, I would expect to get averages that fall in this range here. I might have a hypothetical, I might have a difference from my hypothetical distribution, so a real population that is, say, 2 more than my mean. So my mean I'm assuming is 1 value, and my hypothetical distribution is 2 units further. And if I were to calculate the t statistic under that other distribution, then I would get this red distribution of t statistic values. And so what this is showing me right here is that for this difference in means of 2 units, and for this number of samples, so in this case I only took 4 samples, and for this standard deviation, then my t-statistics line up. And it's really difficult to tell the difference between the alternative hypothesis and the null hypothesis. And so what I can do is increase my number of samples to 20. And when you do that, the null hypothesis t-distribution stays exactly where it is, but the alternative hypothesis for 2 units away in mean shifts over to the right. And at that point, I now can better discriminate between, so if I take averages from the null, they're almost always going to be landing on this side. If I take averages from the alternative, they're almost always going to be landing on that side. But there's still a tiny little bit of overlap. So I might say, well, if I'm not okay with that overlap, in other words, if I don't have enough statistical power, so if the area underneath this curve to the right of my threshold is not high enough, then I might need to take more samples. So now I've got the 30 samples. And at this point, notice my false positive rate still stays the same, that little area underneath this blue curve, but now the red curve is further out even more. And so now I'm pretty confident that I have enough statistical power that, that maybe this test, I don't need to take any more samples. Now there's one other way that I can gain statistical power, and it's by working with this standard deviation. And so if there's a way I can redesign my experiment so that I have less variance in my output, or I can account for some of the variance I have in my output, then what I effectively do is shift the t distribution for my alternative hypothesis even farther over. So I just converted the standard deviation from 2 to 1.5, used the same number of samples, and it further shifted that thing over. So our goal when we design simulation experiments is to determine how many samples we need, but also can we do interesting things with our simulation that reduces the variance. And that might mean pairing up our 2 treatments, our baseline treatment and our hypothesized improvement, and using a paired t-test. That's one way that we can reduce variance. And there are other ways we can reduce variance that we'll talk about later on in the semester. But that's basically the 2 levers you have. Either go through the costly process of taking more samples. Keep in mind, every simulation might take an hour to run. So every sample could be very costly. Or redesign your sim so that you have less variance, but still end up having a meaningful simulation. And so that's the other option. And that just graphically keeps separating out the hypothetical t-values from the alternative t-values. And we can actually graph the alternative t-values because it's a parametric test, because we're making assumptions that we know the distribution. And so that allows us to actually understand what alternatives might look like. In a non-parametric test where we can make no assumptions, we pretty much only have this distribution. And we don't really know what the alternatives might look like. And so hopefully that will become more clear as we go forward. But that's kind of a graphical summary of what's going on with the t-test. So just as a reminder, we're using normality, and that gives us more power, and that makes it a parametric test. And the other parametric tests, so we have the standard t-test and the 2-sample and 1-sample t-test. We've got the paired difference t-tests. You've got ANOVAs, 1-way ANOVAs, 2-way ANOVAs, etc. All things that you should be familiar with from like 380 or 385. Now, if you don't have this parametric assumption, if you can't assume normality, then if, again, I mentioned before, a lot of times you might forget what the parametric or the non-parametric versions of all these tests are, and you can just Google what's a non-parametric t-test, and you'll find that a Mann-Whitney U-test shows up. That was always easy for me to remember because U comes right after T. It's like, oh, it's a t-test, and what's like a more sophisticated t-test? Well, a U-test. And then a paired difference t-test, if you were to Google non-parametric paired difference test, then a Wilcoxon sign rank test would come up. If you were to Google non-parametric ANOVA, then a Kruskal-Wallis test would come up. So as long as you sort of know when to apply a t-test, a paired difference t-test, and an ANOVA, and when you need a parametric test or a non-parametric test, even though these get a little harder to sort of remember, they end up being very easy to find because they're really just meant to be the non-parametric analogs of these. The downside why we don't use these all the time is we lose power. So if you can make assumptions, you gain power. If you can't make assumptions, then you're stuck with these. If these reject the hypothesis, they're fine. But you can't really accept a hypothesis with these very often because they just don't often have that much power. So they're good for rejecting, but not good for making any conclusions if you don't reject. And we are going to use a different term here, exact. And so we use the term exact if it's a parametric test. If all the assumptions are made, we say it's an exact parametric test. And if it's a non-parametric test, we call it exact when there are no assumptions whatsoever. So a chi-squared test is an example that is a non-parametric test, but it is not exact because we have to assume there's a certain number of samples. But a Kolmogorov-Smirnov test is non-parametric, but it's also exact because we make no assumptions. So that's the terminology we'll be using. Parametric, non-parametric, exact, and non-exact. So any questions about those distinctions? Parametric, non-parametric, exact, non-exact, any of this? Just trying to enrich and grow your kind of appreciation for all these different tests, because there will be, in the real world, when you start doing the industrial statistics, not everything's going to be a t-test. Sometimes you have to figure out what other tests to use. But they all do the same thing. They're all these pretty pictures with these things overlapping and not overlapping. All right, so then we also talked about the chi-squared test. So if they really are all these overlapping, non-overlapping things, then where the heck does that come with a chi-squared test? And so graphically, I can summarize that by saying if a chi-squared test is all about counts, how many times did something land inside a bin versus outside of a bin? And if it was all that, just inside a bin or outside a bin, that's a binomial variable. That's like how many times things come up heads or tails. And so if I were to flip a coin 100 times, and I knew the coin had a 5.5% chance of coming up heads, then I could plot the distribution of heads that I got. How many times did it come up heads? And it comes up on average 5.5 times it came up heads. But if I ran this experiment over and over again, sometimes it would come up only one time heads, sometimes it would come up, maybe 14, 13 times heads, but it's almost never going to come up, 20 times or more heads. And so this is describing coin flips. Now, the revelation here was that when you look at this, and as this expected value gets larger, then this starts getting more bell-shaped. And so even though it's a discrete distribution, it starts looking more normally distributed. So here I've got with the expected value is 1, expected value is 2, expected value is 3, 4, 5, and 6. And so if we look at these things for these are all binomial distributions, then I've also put an approximation of a normal distribution on top of them. And we can see that, that there's a significant truncation for 1, 2, 3, 4, and then 5 is when you start getting to the point where the normal basically ends up grabbing all the mass. So the normal kind of covers everything. And by 6, then the binomial really is well approximated by a normal. This is the reason why you can't use a chi-squared test unless you have an expected count of 5 or more. This right here. If you have less than this binomial approximation of the normal just doesn't make any sense at all because you end up getting this truncation. It just does not look normally distributed. But once you hit 5 or more, the binomial looks like a normal. And so what that allows us to do is then replace those binomial distributions with a standardized score. So now we can say, I expected there to be 5.5 coins to land heads in this bin. And I actually got 10 coins landed heads in this bin. How do I sort of capture how weird that result is just for this bin? And if I can approximate the binomial with a normal, I can then replace the counts with a z-score. So I can say, what's 10 minus the expectation, whatever, 5.5, divided by the standard deviation, ended up getting a z-score that goes from negative infinity to infinity. It's centered on 0, and if it is around 0, then it is close to the expectation. If it's far away, then it is probably doesn't match my expectation. And so I've got multiple bins, so I've got multiple z-scores, and I'd like to add them up together. But if I get a negative z-score in one bin and a positive z-score in another bin, when I add them together, they're going to wipe out their effect. So what's the trick we do when we add a lot of these z-scores together? We square them. And that by squaring them, that means that if I get a big difference in one bin and a big difference in another bin, when I add them together, then I maintain that kind of the weirdness of all the bins end up adding together. They don't ever cancel out. And so that's all that a chi-square distribution is it is the distribution of squared standard normals when you add them up together. And so what you're seeing here is these are different chi-squares, different degrees of freedom, and this is effectively the number of bins minus 1. And so this is saying that if I only have one bin, then I know that my differences will never be negative, but the differences are going to probably be low. As I go up to 9 bins, then I know that my differences will probably never be 0 because it's really hard for me to get exactly the expected value in all of the bins. But they're probably not going to be higher than, say, 7 or 8. And so that's what this red line is kind of showing us. We expect the accumulated squared z-scores to be around 7 or 8 when I've got these 9 degrees of freedom. And so that's what we're kind of seeing here. And so we can convert this chi-squared into effectively an accumulated z-scores, and that's all I'm doing here. And what this plot here is on this side, this is the chi-squared statistic, and on this side, this is the p-value. And what this is sort of showing us is that for a given p-value, let's say 0.05, which would be like down here, as I increase my degrees of freedom, I get kind of more tolerance for difference. And so what we're basically saying is if you add more bins, then we're going to let your chi-squared get larger and larger and larger before we reject the hypothesis, because you've got more opportunities, more degrees of freedom to vary. And that's sort of just capturing visually what's going on here. So when you look at a chi-squared, it's just, again, effectively the squared z-score under than your number of bins. And that's where we get that statistic right there. So I did a little thing in MATLAB where I said, well, okay, so let me put the chi-squared for a particular distribution. And then I'm going to take a distribution and I'm going to just multiply all their probabilities by 98%. So it'll be a slightly different distribution. And then I'm going to run a bunch of chi-squared tests on that slightly different distribution. And that gave me this histogram of chi-squared values under my slightly different distribution. And then I said, let's then now take the distribution and multiply it by like 80%. So it's a very different distribution, a very different number of expected counts, and then run a whole bunch of chi-squared tests for experiments on that alternative distribution. And so we can see that when the distributions are close to the hypothesis, then I get something that looks like a chi-squared distribution with that number of degrees of freedom. And when it's far, then it's pretty far off here. And this, again, looks like that picture that I was just showing you, where you've got the test statistic under the normal, or under the null hypothesis, and you've got a test statistic under some alternative hypothesis. And so most of the time, this alternative test statistic is on the right-hand side of this critical threshold, but sometimes it's on the left, but hopefully it's on the right more than it's on the left. And that makes for a good test. So that's the chi-squared test. So any questions about the chi-squared test or where it comes from? Hopefully it's a little less mystifying where this funny squared difference divided by an expectation comes from. It's just a squared z-score. Okay. So we use the chi-squared for two things. We either do so-called tests of independence. So you might run a simulation where you take frequency data out. We'll talk about that today, how frequency is one of the outputs ARENA can give you. And then your question might be that, all right, so I'm interested in knowing how many people fit into, I don't know, 3 categories at a restaurant. Maybe people who spent a lot of time waiting, people spent a moderate time waiting, and a slow amount of time waiting. And so I might want to study the frequency distribution across those 3 categories. and I make a change to my operations of my restaurant, and I want to know, did I effectively change the frequencies? Well, it's random, so in one simulation, I'm going to get some frequency distribution. In another, I'm going to get some frequency distribution. I want to know, are those plausibly coming from the same distribution, or did I make a difference and effectively change the frequency distribution? And so this chi-squared test of independence allows you to sort of see, is there a difference in these two frequencies? So we're not actually testing for goodness of fit, we're testing to see, does this frequency distribution look any different than that one? And that's what we use a chi-squared test for independence for. But when you have very low numbers of counts, then you can't use the chi-squared. And so there are these alternatives, which are these exact tests, like the binomial test, the multinomial test, and the Fisher's exact test. And so if you find yourself wanting to know, is my frequency distribution different under one condition or another, and you have a very low number of counts that have shown up in your experiment, then you should consider looking up these alternative tests, because this chi-squared may not be applicable. Now, what we've seen the chi-squared being used for is the goodness of fit test. And in that case, it's this expected number of counts has got to be greater than or equal to 5. When it's not, we can use the Kolmogorov-Smirnov test, which is this exact test because it makes no additional assumptions. The critical values become a little hairy when you start estimating parameters. So that's one reason why the KS test isn't a great one to use. And the way it works is it basically studies the difference so its test statistic is the difference between an expected CDF and the sample CDF. And you say, well, how do you come up with a test statistic for that? And the idea comes from this mathematical construct called a Brownian Bridge. And a Brownian Bridge is this idea that if I start at 0 and I end at 0, but I'm allowed to stray and follow a random path, given that I have to end at 0, how far away could I get while straying? And it turns out that we can mathematically define that. So if you say, well, you can only take 5 steps on your path, how far could you possibly get away, given that you need to start and end in the same place? Well, that is saying the same thing about the sample CDF. It always has to start at 0. It always has to end at 1. So how far could it wiggle its way away? And we can quantify that, and that's the way you get the test distribution for a chi-square or for a KS test. It's this Brownian Bridge approach. But fortunately, that's all been done for you. It's all stored inside the input analyzer, and all you have to do is use the test. But behind the scenes, that's how that test statistic comes from. Yeah.
So is it like a measure of distance between the CDF and then all those other things?
And the sample CDF. So if I have data and I sort it, and then I plot the sorted data against its rank, then I end up getting an approximation of the CDF of the real distribution. And so we are estimating we know that even if data were sampled from the red line, it's going to vary a little bit. So the question is the variance expected, or is it from a totally different distribution? And if it's from a totally different distribution, it may stray significantly far away. And the Brownian Bridge would say that the amount of distance you strayed away indicates that maybe you actually weren't even close to this path to begin with.
So it's basically like the distance between the CDF and the QQ plot?
Well, so the QQ plot is sort of related to this. That's like, this quantifies what's going on in the QQ plot. Yes, good point. All right, and so, but in your modern statistical tools, you may not find the KS test. If you don't find the KS test, then look for the Anderson-Darling test, which is actually a more powerful test. The only downside of the KS or the Anderson-Darling test is that it really does have to be tailored for whatever distribution you're testing against. And so, fortunately, it has been tailored for most distributions we care about, but it does have this sort of one downside. Now, if you are just testing for normality, you should short circuit to the Shapiro-Wilk test because it is the most powerful test to test for normality, which means if it does not reject normality for your data, under it, you usually are allowed to assume your data are normal, at least when you also pair them with a QQ plot. So if you visually can show that your data on a QQ plot look normal, and the Shapiro-Wilk test does not reject them, then you can move forward assuming that your data are normal. So if this was a more in-depth statistics class rather than just a simulation course, then I would require you to do a QQ plot and a Shapiro-Wilk before every t-test, before every ANOVA, because that's the way you do it in real life. Because you cannot apply a t-test or an ANOVA until you confirm that your data are normally distributed. Here, we're sort of assuming, and for reasons that we'll talk about today, that the data coming out of the sim are usually going to be well approximated by normal anyway. But as you move forward, you should be a little more careful. And so leaving this class, remember that these things exist because you're going to be expected to know to use your QQ plots and your Shapiro-Wilks before you go into any of these parametric tests. So any questions about the caveats behind these t-test, chi-square test, etc.? All right, the last thing that I wanted to remember from the last lecture was this multiple comparisons, which we'll see pop up in ARENA's output analyzer later in this lecture. But if I've got a sim and I measure 3 different things on the output, and I've got 2 different versions of the sim, I've got my baseline sim, and I've got my sim that I think has got an improved operation. And I want to say, is there a difference between these 2 sims? I could run a t-test on this one, a t-test on this one, and a t-test on this one. And I might find no difference here and here, but I get a difference here. But the worry is, if I had like 50 outputs and I did a 50 t-tests, eventually I'm going to find a difference just by random chance. Because the false positive rate for every t-test is 5%. So if I flip a coin with a 5% chance of coming up heads, if I flip it 100 times, it's going to be crazy if I don't come up with 1 head. So that's the same thing that goes on here. A t-test is really just, or any statistical test, is really just a weighted coin that comes up in the sort of negative, the false condition 5% of the time. So if you flip that weighted coin too many times, trying to conclude the same thing, you'll eventually find the difference when there isn't actually a difference there. And this is the so-called multiple comparisons problem, which some people sort of summarize as the fishing problem. So if you go fishing, eventually you're going to catch a fish. And so how do we deal with that? If you're going to compare 2 different simulations, but you're going to run multiple tests to compare those simulations, each individual test's alpha, each individual test false positive rate has to be made smaller or so that your total alpha for the whole group ends up remaining at 5%. And so what we do is we just divide the alpha for every individual test by the number of comparisons. And so you want a 5% rate for comparing your whole sims, but you're going to compare them in 10 different ways. Well, then you better actually use a t-test with 0.005 probability of finding that false positive, because in that way, when you go fishing, there's only a 5% chance you're going to find a difference that's not actually there when you look at the entire family of comparisons. And so that's one way that we solve this problem. Question?
And you said that that's to make sure that alpha stays at 0.05 for the whole group.
Right.
Okay.
Right. So if I'm comparing the 2 sims, how do I know that my protocol of doing 50 comparisons, that becomes a new hypothesis test. So if I'm building a hypothesis test out of multiple hypothesis tests to make sure that the alpha for the family hypothesis test is 0.05, I have to adjust the alpha for the individual hypothesis tests. And that's the so-called multiple comparisons problem. And there are other solutions. And so when you leave your undergraduate degree, if you go off and do either a master's degree or if you start working in a place that does a lot of statistics, then you're going to start seeing these terms like post hoc test pop up or MANOVA instead of ANOVA. And these are tests that have been designed to be even better at this multiple comparisons problem than this so-called Bonferroni correction. But in a pinch, if you don't have these available, or you're using a statistical test where none of this extra work has been done on, then you can always apply this Bonferroni correction. It's conservative, which means that your family alpha will probably be even lower than 0.05, but it at least won't be higher, because having it higher than 0.05 when you think it's 0.05 is much worse than having it lower than 0.05 when you think it's 0.05. Any questions about that? Yeah.
What is the K in the Bonferroni correction?
That is the number of comparisons you do. So in my example, it would be 3. But it depends. So it could be, if you decide to do every single combination, I've got 4 different models, and I'm going to compare each model. Like I might have 1 output, but I have 4 models. And so I'm going to compare model 1 to model 2, model 1 to model 3, model 1, and I do every single combination. Then K becomes however many comparisons I did. And that's what, if the ANOVA does that for you, is the ANOVA says, if I have 4 different models, the ANOVA will say, there is a difference across these 4 models. And then the so-called post hoc test then more efficiently, so not the Bonferroni, ends up telling you this, model 1 is better than model 2, is better than model 3, is better than model 4. And so these are, like the Tukey test and Fisher's LSD, are things that we use to sort ANOVAs after they're done. But if worse comes to worse, you can always do this approach and then do pairwise t-tests instead. Question?
Do comparisons always come in pairs, or is it usually like by 3 by 3 or
Well, so I guess that's what I'm kind of getting at. So a t-test is defined as pairwise. So it's either data against hypothesis or data against data. But the ANOVA, if you think about it, is an example where I've got, say I've got 1 factor but 4 levels. Well, in that case, I'm comparing all 4 levels simultaneously. So the ANOVA, and then the MANOVA gets even more complex, but these are tools created to be generalizations of the t-test that aren't just pairwise. But when we talk about a t-test, which is kind of like you can build a lot of these tests with t-tests, then it ends up being pairwise, and that's why you have to do this correction. You don't have to do the correction with things like an ANOVA because they're kind of already baked in not to be pairwise. It is the pairwise nature of a t-test that requires us to do this correction. Any other clarifications about this multiple comparisons or MC problem? All right, so then the last thing that I want to mention before we get on to new stuff is I just want to highlight, I've been talking about alpha equal 0.05, and I hinted at this last time. In an engineering application, this may not be the optimal threshold for you. So in a scientific application, it's actually kind of arbitrary, this 0.05, but it's sort of been convention that 5% false positive rate is what you accept from a scientific study. But if you're not doing a scientific study that you're going to publish and no one else is ever going to work on again, if you're doing some prototyping in an operational context, and you know that if you detect that there might be a difference, from your operational perturbation and the baseline, and you don't want to accidentally miss one of those differences, and you've got a boss who's willing to say, if you show me there might be a difference, I'm willing to dump a little bit more money in to further investigate. In that case, you might want to set your personal alpha at 10%. You might be able to tolerate a higher false positive rate. In other words, this is saying 5% of the time, you're going to tell your boss there was an improvement in performance when there actually wasn't. And that might be, maybe your boss is okay with you coming back when being wrong 50% of the time. Probably not, but maybe it's at least higher than 5%. And so if you think that they want you to find a difference and they're willing to put more money into actually seeing if it's a difference afterwards, then maybe you don't need to be so conservative. So don't always take this 5% as gospel. In the machine learning community, they actually are just sort of figuring out, they sort of forget about this threshold, and they just sort of actually pick the critical statistic just based on some other optimality criteria. And so, picking your discrimination threshold, there's a lot more wiggle room than we've led you to believe so far in your statistics courses. So keep that in mind that maybe you'll need to adjust this. In this class, when in doubt, it's 5%. But moving forward, it's possible that you might want to increase that to 10%, for example. Or maybe you're working in a pharmaceutical application or something like that, and there's a reason why you might want to make it 1%. So, that is another lever that you have to move around. But do it before the experiment, not after. If you do it after, that's kind of like p-hacking. So that's like trying to find, it's like, oh man, I'm going to get fired if I don't find a difference. Well, I'll just adjust my alpha until the p-value I had becomes significant. That's not right. But if you do it before you do the experiment, say, I'm willing to tolerate 10%, now I'll do my experiment, then it's legal to do. And you just, give the caveat, I might be wrong 10% of the time. So any questions about that? It's about the setting of the thresholds. All right, so let's move on. And so stats in lab 9, you're going to start working with the output analyzer. So we're going to start actually trying to say meaningful things about simulations. In lab 9, we're going to give you a model that's already pretty complicated. You're going to make some modifications to it, and then you're going to do some tests on that using things like the output analyzer. So you have a complicated simulation. And let's say, in this example here, you run the sim 3 times, replication 1, 2, and 3, and it generates 5,000, you run it for 5,000 minutes. And so the whole simulation runs for 5,000, each of these 3 replications. Now, for reasons that we'll talk about later, I might actually want to take each replication and actually generate 5 batches out of it. So I might want to say, well, what are the average value of my response variable for the first 1,000 minutes, for the second, for the third, for the fourth, for the 5th 1,000 minutes? And so within a replication, I get 5 numbers out. And across replications, I get 3 sets of those 5 numbers. And we notice a lot of variability. Across replications, we see variability, and then within replications, we see variability. And so wherever we see variability, there's a room for statistics. But the problem will be that within replication, these numbers are not independent. These numbers, this could be the average inventory level in week 1, and this is the average inventory level in week 2. Well, you know that the inventory level in week 1 is going to have some determination of the inventory level in week 2, because week 2 starts with whatever week 2's inventory was. So there might be correlation between these within a replication, but if we choose different random number seeds across replications, then because this uses a different seed, then these numbers should not be related to these numbers. So because we have independence this way, we might expect that all of our t-tests, ANOVAs, or whatever might be applicable across. But within replications, we might need to be more careful because we will not have the independence. And so I can't take a bunch of within replication data and compare it to other within replication data and make comparisons there because they don't have that independence. And so that's what we're getting into. How do we deal with these 2 sources of variation, within and between? So there are questions of what do I mean by within and between? So, data out of a single replication versus data across replications. Okay. So when I have independence, then I can use this standard error of the mean. So I can basically calculate a mean, a point estimate like this one. Yeah, question?
So you said that within a replication that are not independent, right?
Right, they could be correlated, so they're not independent within, but they are across. And so if you have independence, we can calculate a point estimate. We can average over those independent samples. And we can then calculate the standard error of the mean, which I talked about last time as a way to build up to where the heck the t-test formula comes from. And the standard error of the mean captures the variation in my estimator. And so the idea here is if I run this experiment over and over and over again, so let's say I run 3 replications and I average these numbers. And then I run another 3 replications and I average those numbers. And I run another 3 replications and I average those numbers. Those 3 averages that I just talked about, averaging the first 3, averaging the second 3, averaging the third 3, are not going to be on top of each other, but they will be related to each other. And the variance in the estimator is this so-called standard error of the mean. And it turns out that if you solve mathematically for this, it's just the standard deviation of the y variable divided by the square root of the number of samples you use in the point estimator. And so this standard error of the mean, as the number of samples gets higher, then you collapse on the true mean of the distribution. And so that's kind of a good feature. So even though variance in the distribution doesn't go away, variance in the estimator does go away. So that's the difference between the standard deviation of the distribution and the standard deviation of the estimator. So that's what whenever you hear somebody say error bars or standard error, they probably don't mean standard deviation. They probably mean the variation in the estimator. So that is a critical difference. And so you have to make sure that when you calculate the standard deviation, you use the n minus 1, just because you're using the estimator as your estimate of the average. And so that's kind of important, but usually these are calculated by a statistical tool for you, so you're not manually doing this. But if you do manually do it, again, make sure you do n minus 1, or else this will be a bad standard deviation. All right, so this point estimator is best suited when replications, when you're moving across replications. So when you're averaging within replications, then it's harder to sort of say what this estimator means. Mean is sort of a funny term to work here. What is the meaning of this estimator? Only when it's across this replication data. So across replication data, they're independent, they're identically distributed, and normally, they are normally distributed because very often, if you take data out of a replication, it's very often the sum of a lot of things. So we might say I simulated 5,000 customers, and for a single day, the average time a customer waited in line was going to be, all of the times, the 5,000 waiting times divided by 5,000. Well, that means that that sample for that single replication will be very likely by the central limit theorem to come from a normal distribution. So for these reasons, across replication data usually meet all of the assumptions needed to apply a t-test or an ANOVA. And so this normally distributed one, you should probably double check, but it's very often the case that data from a replication will be normally distributed, and if it's across replications, these two other things will be met, and so you can apply any parametric test that you'd like that depends on the normal distribution. Now, within replication data, we have this issue that my samples may not be independent. So I mentioned the inventory level thing. So if I have the inventory for 1 week, and I use that as a data point, and then the next week in that same replication, those two inventory levels will likely be related to each other. I'll at least be able to predict a distribution of inventory levels from 1 week, knowing the inventory level from the previous week. And so most of our tests are built on independence, and so we probably won't use these data in that same way. Or if we do, we need to make sure we do things like, well, I'm only willing to compare the first 5 weeks with maybe after I'm going to let the simulation run and take another 5 weeks that are 20 weeks later. If I put enough of a gap in between them, then maybe my average from one set will be different than my average from the other set. So, so that autocorrelation is going to be something we'll deal with, and we'll talk about that more in the next lectures in this unit. So that's one problem we have to deal with. The other problem we have to deal with is initial conditions. So I've gotten questions about this. People say, well, if I turn my simulation on, I notice that the queue lengths initially are empty, and they take time to fill up, and then they end up staying kind of set at a certain amount. So, how do I know, is there a way for me to initialize the queue lengths to a particular level so that I don't have to wait for them to kind of come up to their normal operating level? And we'll talk about that in this unit, because that is a source of what we'll call bias. So in other words, if I average over a single replication, if the first half of the replication was just the queues getting filled up, and I don't actually trust that data, because in real life, I assume that my queues have already reached steady state, then I need to get rid of all of this initial data as the queues start filling up. So that's the other issue with initial conditions. So we have a challenge to independence, and we have a challenge to bias. And those are the things that we'll deal with in this unit when we talk about getting data out of these simulations. So are there questions about what I mean by autocorrelation within a replication and the potential issues of initial conditions within a replication? Again, this will become more concrete as we move on. So now there are other ways that I can estimate. I don't have to use an average. I don't have to use an arithmetic mean. I can also average, take quantiles. I can say, what is the value that is above 90% of all values that come out of the simulation? What is the 90th percentile? I can also take interval estimators. So I can say, what is a confidence interval? I don't actually care about what the estimated point estimate of the mean is. I want to know what the confidence interval around the mean is. And we'll talk about that, what we interpret, how do we interpret confidence intervals. And as we move forward in the class, we're going to shift away from point estimators and on to interval estimators because they're much more informative and they're much more honest about your confidence in your simulation. So we're going to start there and end here, by the end of this unit. All right, so any questions about any of that stuff, the definitions, before we get to make things more concrete? So the two types of sims that you work with are terminating and non-terminating, or those are two types of systems, and we simulate them with transient and steady state. So I'm okay with you equating these two, terminating and transient, and non-terminating and steady state, and swapping them and using one for the other. Sometimes you might refer to a steady state system, but I guess formally, if in the book work, it's a non-terminating system is simulated by a steady state simulation. And let's see what I mean by that. So a terminating system is a system that runs up until an event E at a certain time. And I care about when it starts and when it ends. And I average over that entire span of time, from the beginning till the end. As an example, a bank isn't open for 24 hours. It opens at 8:30 a.m. It ends 480 minutes, it closes 480 minutes later, and there's no customers present when it opens, and there may be customers that get kicked out of the bank when it closes. And I care about all of those things. I care about how quickly customers start to accumulate. I care about how many customers are left at the end of the day. I care about the entire interval. This is what I would call a terminating system, and I would use a transient simulation to simulate this. There's another example. So this call center example that you saw in a previous lab, if you go into the run setup for the call center example, in most of the sims that you've seen so far, there's a replication length that has been filled in. Here they put infinite in there, and they say condition. You should stop the sim when the current time is greater than or equal to 600, and when the number of customers in the trunk line is equal to 0. So what this is saying is that the call center, if nobody's waiting on hold, the call center will end after 600 hours. But if someone's waiting on hold, even if you're over 600 hours, they'll wait until you've gotten rid of everybody who's waiting on hold. And only at that instant, when there's no one waiting on hold, will the simulation end. So in this case, this is still a terminating simulation. In fact, I might be interested in how much longer I have to keep my call center open just to get rid of these people waiting on hold. That might be a performance variable that I want to measure. So even though this doesn't end at an exact time, we still view it as a terminating system because it ends when a condition is met. And I care about the system when it starts, and I care about the system when it ends. So that's what I mean by a terminating system. And it's simulated by a transient simulation. So that a transient simulation is one where we care about the entire simulation, not just the part right at the end. Now I can contrast that with a non-terminating system, and so I study the steady state properties. So I don't care about the system when it starts. I only care about the state that it sort of settles out at. And I stop it at an arbitrary time that is just long enough to ensure that it has reached steady state. So I might stop it at some large number where I think all the transients have died out, Or I might stop it when I detect that some dynamical variable that's normally moving along has sort of settled down to one value. And when it settles out and doesn't wiggle very much, I might say I've reached my steady state condition, and I'm going to take my statistics within a small window, just the end of the simulation. So I get rid of all of the data during the transient. And that's why I refer to this as a steady state simulation. I throw away the transient data. Examples of this is like an assembly line that effectively runs for 24 hours. It only fails infrequently, and we don't care about the operations during those times because we know that it'll be back up and running and then run for another 3 months before the next failure. Telephone systems never go offline, so we might model them in this way. Emergency rooms, 24-hour grocery stores. So there certainly are changes in activity throughout a 24-hour grocery store, but we don't ever have to worry about simulating when they close and when they open. We just sort of simulate how they run. So it might take Walmart an hour or two to get back up into speed if they do ever have to close down. But after that hour or two, they're going to be open for months on end. And so I just simulate the months on end, and I throw away the equivalent of the hour or two inside the simulation. So graphically, I can summarize these two as saying the terminating simulation is one where I have a natural start for some of my response variables, and I watch how that response variable comes up, and maybe it reaches some steady state, or maybe it does something else, but I care about the entire trajectory. So that's my transient simulation, which is a model of a terminating system. And then the alternative is I am modeling a non-terminating system, so I still have transients because I have to start my sim, but I have to determine a point in the sim that after which I pay attention to the data and before which I throw away the data because it is meaningless, it doesn't have anything to do with the real system. It's just there because I had to get the simulation started. So this is the steady state simulation of a non-terminating system. Are there questions about this distinction? Somebody give me an example that I haven't already mentioned of, say, a steady state system. Somebody think of another steady state system. Or I should say non-terminating system. We would use a steady state simulation for. Anything? Take 30 seconds, talk to your neighbor. Come up with an example of one of these. All right, so let's bring it back. So who has an example of a terminating system that you might model with a transient simulation? Any yeah. So sales per, so okay, yeah, I like that. So that's like a long-term simulation. So you might say that we were started at some market penetration, and we do a new marketing strategy, and we want to see, based on our model of how people incorporate information for our marketing strategy, we'll use a transient simulation. And our simulation, which maybe models the psychology of people, how they spread information or whatever, shows that our market penetration now rises and reaches a new level. And we're interested in how long it takes to rise. I like that. That's a great example. Any other examples of, say, a non-terminating system that I might model with a steady state simulation? Yeah. Hospital, yeah, I think I mentioned a hospital, so like a 24-hour hospital would be a great example. So an urgent care is probably more here, but an emergency room is probably more over here, where my simulation is going to initially have no beds full. And so my simulation is going to take a while for me to reach the kind of steady state for how many beds are full in the hospital. But in reality, if I go to any hospital, there's always going to be somebody in a bed. So I throw away this part, and I only go forward this part.
Okay, wait, so for the steady state, simulation, you still have to put together data. It's just that
Yes.
we only care about after it's up and running.
That's
and then for the terminating, we care about from the very beginning to when it's up and running.
When it terminates, right. Next question right there.
Yes. Basically, you said that the initial conditions for the non-terminating system is it gonna be 0?
Well, the initial, there have to be something. But the idea is that the contribution of those initial conditions, if I included these data and tried to say, what's the average of this performance variable across the whole replication, if I were to include these data, it would pull this estimate down. And this estimate that's been pulled down would be improperly pulled down. We refer to this as bias. So I need to get rid of this to get rid of the bias.
So you're always gonna get rid of initial conditions in a steady state simulation.
That's right. And in fact, if you go back, it's hard to read on this projector, but there's a warm-up period in your run setup in Arena. And that warm-up period is you telling Arena when should it start looking at your results. So that is, you are effectively saying, when do you stop throwing away data and start paying attention?
And then is there a way to calculate the warm-up period?
Yeah, and that's what we'll get into in this unit.
Okay.
Is there another question or comment?
Just another example, like power plants for steam.
Yeah, right. So power plant's another example. Occasionally power plants do go down. Maybe you're worried about fire in California, so you shut the power plant down. And it's going to take time to spin everything back up. And when power plants come back up, there's all these cool transient effects, like all the air conditioners come on at once, and that often will take power plants down because they normally like a normal operation of air conditioning is they're usually phased. Like I turn my air conditioning on, then you turn yours. But when you turn all the power back on, all of our air conditioners come on at once, and often that takes the power down again. So it takes a while for them to figure out how to get the power plant up. And and likewise, our sim might take a while for us to get rid of all those transients. But in the end, we don't care about that because it's so rare that we really just care about this operational period. So we're going to throw away that data. And we will learn how to throw that data away in this unit. All right, so let's move on with that then. So the main focus of the rest of these things, so most of it has sort of been covered here, but I just want to give an introduction to this Arena stuff for one. So you're going to go into Lab 9, and you're going to start getting data out. Now, if you really don't like the data handling facilities of Arena, you can just get raw data out of Arena and analyze it yourself. And there, I have a video online that tells you how to use these read-write modules to do that. So I'm not going to go into detail on that here, but know that in the advanced process panel, there is a read-write module that basically allows you to write out to a CSV file. And whenever an entity passes through it, it can write a bunch of columns to your CSV file, and you can get whatever sort of raw data you want out of your sim, and then go into R or MATLAB or whatever tool you like, Jump, etc., and run your own stats. Now, if you instead use these record blocks, then there's ways in which we can make Arena do some of the stats for you, beyond what you've seen in just the reports, and that's what I'll kind of show you here. So the record blocks, which you've hopefully seen or noticed in some of the models you've already been working with, an entity flows through them, and when the entity flows through, you can then take a record of a number of different things, and I'll define these things on the next slide here. So when one entity goes through, it can take a snapshot of as many measurements as you want, and they get recorded in memory of the simulation, and then later they'll either be aggregated in your reports, or you can get that raw data out and analyze in the output analyzer. That's what we'll see here. So if I were to zoom in on this record block, we can see that there's count, time interval, time between, and expression. And they record to different types of memory inside Arena. So there's two types of memory inside Arena. A tally, which is a list of records, or a counter, which is a single number that gets incremented and decremented as you wish. So in the case of tallies, like time interval, basically whenever that entity goes in, it will calculate the difference between the current time and some attribute that's been stamped on the entity. So like, when did it enter the system? When did it enter a part of the system? And this time interval will subtract how long it's been since that spot there, and it will add it to the tally that you specify. So you get a list of these differences that you can then analyze later. Time between basically is whenever you enter one of these record blocks, it keeps track of the last time you went into one of these record blocks and then adds a record of that time between. The expression allows you to put an arbitrary arena expression in, and it'll save that. And then the counter allows you to increment or decrement a counter by however many you want, as long as it's an integer. So you can go up 5, down 2, and it'll keep track of that. And all of that can end up getting analyzed in the output analyzer, which we'll get into here. And I may end up picking up next time, starting with this, because next lecture will be a little shorter than this one anyway. So maybe what we'll do is, because we're 43, is why don't we, this is a convenient place to stop. So let's do today's attendance exercise. We'll pick up right here, and then as you work with Lab 9, you'll start going in, you'll use these statistics with the output analyzer, which I'll talk about, in order to do interesting things with your data. So that's over here. But all right, so let me get back to the attendance slide here. And so the attendance exercise for today is what type of system, and you can use either term, either the simulation type or the system type, is one where we care about the entire trajectory from the initial condition to the end. So we mentioned there are these different terms that we use either for the type of simulation or the type of system. And I'm okay with using either of those terms, but just the one where you care about the whole trajectory. That's our attendance exercise for today.